So ionic bonding. Ionic bonding is the electrostatic attraction between positive and negative ions. It holds together cations, positive ions, and anions, negative ions in ionic compounds. Common cations we already know: sodium, calcium, aluminium. Most of them are metals. Ammonium ion. This is what is it? What is this called? Polyatomic ion. Was this called polyatomic ion? We went through it yesterday. So things that
Did we
have
go through this?
yes, no, not through this, but some things are ions, but they have more than one atom. So those are
Or
called.
radicals?
So I said radicals, but
Oh
you
yeah,
yes, but it
yeah.
was
They are radicals or polyatomic ions.
yes. So they are polyatomic ions. Common anions we already know: chlorine, oxygen, nitrate, and sulfate. So these are the most common ones. Dot and cross diagram. The simplest ionic compound contains metals, ions, and non-metal ions at GCSE. You use the model for ionic bonding based on electron transfer. Outer shell electrons form a metal atom from a metal atom are transferred to the outer shell of a non-metal atom. So this is the most basic form of ionic compound. Positive and negative ions are formed. The ions formed uh, often have outer shell with the same electron configuration as the nearest noble gas. So they mostly have the same configuration as the nearest noble gas, because that is the purpose of making making bonds, right? Everybody wants
Yeah.
to have their perfect configuration like a noble gas. In dot and cross diagram, the electrons in the original atoms are shown as either dots or crosses. It is then easy to work out the charge on each ion and to account for all electrons. Okay, we'll see an example of potassium fluoride. Figure 1 shows electron transfer of the outer shell electron in a potassium atom K to the outer shell of a fluorine atom. You already know that the electron will go from a metal to the non-metal, forming a potassium positive ion and an F negative ion. The square brackets show that the charge is spread over each ion and that the ions are separate entities. Only the outer shell electrons are shown below. The inner shells are full and are not involved in bonding. The electron structures of potassium positive and fluorine negative ions formed are now the same as the nearest noble gas. So it's shown by a cross. So the outer shell of potassium is shown by the cross. The outer shell of fluorine, in which electrons are shown by circles or dots. This cross, which is an electron in potassium, will go to fluorine so that it makes whatever noble gas was before it in the atomic number. So whatever it is, it will make the electron configuration of that when it gives away its electron to fluorine. And fluorine will make the electron configuration of the noble gas that is after it, because it gains an electron. So again, they have put the brackets just to show that overall it has a positive charge now, and fluorine overall has a negative charge.
Yeah.
Uh,
So, just a question.
yeah.
So, when potassium loses one electron, the electron configuration is the same as fluorine.
When potassium loses one electron, the
Is
electron
the electron configuration the same as fluorine?
the electron configuration will be the same as what was before it in periodic table, because it has now lost an electron. So it will be
Oh,
closest
yeah.
to the noble gas that was before it.
So, when potassium loses one electron,
So one number less.
is the same as argon.
Yes, it becomes exactly the
So
same.
then instead of can you just write AR?
Yeah. Can you just, yes, if you have to write the shorthand version of this, you can just write this AR, and that will be the whole configuration of potassium,
Of
or
the
potassium
potassium
ion. Yeah.
ion.
Yeah.
So do you need to then write a AR plus?
I don't, oh, yes, that is
Because
what,
then people will think that it's an actual argon.
yeah, yeah, that is what I am thinking.
But I
But
think if you
but
write AR one plus, then they will know that it's a potassium
I
ion.
am not sure if they have shown us anywhere, how to write the electron configuration of ions. Did they show it anywhere in the previous topic?
I'm not sure.
I saw ions somewhere, but electron not here. Configuration of atoms. Shorthand configuration, the electron configuration of ions. So positive ions, okay, bro. So they don't show the electron configuration. Positive ions are kind of formed when I'm not sure if you have to write any negative or positive sign anywhere because electron configuration only shows electrons. It does not even consider what the proton number is or what how many protons are there. Okay, if you look here now, it's even clear. You see calcium 2 positive. They don't show that it has any 2 positive or anything here. They just write it as.
No, oh yeah.
So if you have to write, you'll just write AR. Or if you have to write a shorthand notation, you just write AR. You don't need to show any positive or anything. Just
But
write.
then the what if like the people think that I'm writing an actual argon
No, but
instead of a potassium ion?
so I think that will be the question that that will be in the okay. Okay, if for your question, I have a counter question. So
Okay.
if calcium, if you write calcium 2 positive,
Yeah.
electron configuration, do people think that it is what comes to atomic number before calcium? What's that? Can you look at the periodic table and see what's the two atomic number before calcium?
Argon.
Argon. Do people think that when you write this, do people think that it's argon?
Yeah.
Yeah.
Why will they not think it's argon?
Yeah. So this answers your question as well, that we don't care what people think. We just write what is
Okay.
right, all right? Because they have also written it like this.
Yeah.
You don't need to worry about that. Just write it. If they ask you write the shorthand notation, just write AR. That's it. If they don't say specifically write the short notation, you should not write the shorthand notation. You should write the whole thing. All right.
Yeah.
So that's it. You don't need to worry about what people think of it because they have asked you the question, so they know what you have to write. So you don't
Yeah.
have to worry about it. Where were we? So yeah, so we know that electron goes there, then both of them are to their closest noble gas. They have the electron configuration of the closest noble gas. This one is just like neon, this one is just like argon, and that's it. What are the charges? They have thrown this is positive one, this is negative one. That's it. So then they have shown the example of magnesium chloride. So magnesium has two electrons to give away. It's in group two. It gives one electron to each of the chlorine. The chlorine, all of them now have they have the electron configuration of argon after that. This is slightly confusing. Why does it?
They're
This
all argon.
they are not all argon. So what's the atomic number of argon? Is it 18?
Yeah.
What is above argon in the noble gases? And is it 10?
Yeah, neon.
So this is not argon, this is neon, right? So
No, yeah.
there's
Why does it say argon?
this is a typo. You should
Yeah.
email the company that wrote the book.
Yeah. It was made by Oxford.
You should email Oxford. Maybe they'll just they will just give you admission in engineering there. They'll say just uh, correct our books. All right, so this is closest to now after giving away two electrons, this is closest to neon. So this will have an electron configuration of neon, and both of the chlorines will have the electron configuration of argon. All right. So we know that this is negative one, this is negative one, this is positive two after giving away the electrons, and that's that. Structure of ionic compound. Although it is convenient to look at ionic bonding acting between a small number of ions, each ion attracts oppositely charged ions in all directions. So it again giving you the same example of sodium chloride, and also they have given the same example. We'll just see. The result is a giant ionic lattice structure containing billions of ions. The actual number only determined by the size of the crystal. The giant ionic lattice of sodium chloride is shown in figure 4. A giant lattice is a key structural feature of all ionic compounds. Each
So my
sodium
teacher said that you can't call it a giant ionic lattice anymore. He said that you have to call it a giant 3D ionic crystal lattice.
So it may be a new terminology that they want uh, you to say. Maybe this is outdated or something. That's why he said that.
Okay.
So just do what he says.
Yeah.
Just call it what he says because he obviously he'll be right. So maybe
Yeah.
they don't use it anymore. All right. So this
Okay.
book may be an older revision of the book. So that's why.
Okay.
So, all right. So, what they are saying is that mostly ionic compounds make big letters. That's why I told you we use the empirical formula and write NaCl. Otherwise, each sodium is being surrounded by, I don't know. Okay, each sodium ion is surrounded by six chlorine ions. Each chlorine ion is surrounded by six sodium atoms. And they don't know which one is their sodium and which one is their chlorine because all of them are identical, right? All of the
Yeah.
sodium are positive and all of the chlorine are just negative one. So all of them are attracted towards one of them. So each sodium is surrounded by six chlorine. So it attracts all of them in the similar way as yeah, in a similar way. And each
Yeah. Yeah.
chlorine is surrounded by six sodium atoms, so it attracts all of them in a similar way. So there's no biasness here. So all of them are same.
Yeah.
So each ion is surrounded by oppositely charged. Each ion is surrounded by oppositely charged ions forming a giant ionic lattice. So that's that. So this is they are just telling you how what does the structure of ionic compound looks like. So I think most of them look like giant lattice, not giant lattice, whatever you said.
Oh yeah, a giant 3D ionic crystal lattice.
All right. So it's just like that. It's a king, and you have to say all of the names. Okay? So it looks
Yes.
like that. So he's just giving respect to salt for some reason. I don't know why. Okay. The properties of ionic compounds. So the physical properties of ionic compounds can be explained in terms of the giant ionic lattice structure and ionic bonding. So melting and boiling points. Almost all ionic compounds are solid at room temperature. At room temperature, there is insufficient energy to overcome the strong electrostatic forces of attraction between the oppositely charged ions in the giant ionic lattice. High temperatures are needed to provide the large quantity of energy needed to overcome the strong electrostatic attraction between the ions. Therefore, most ionic compounds have high melting and boiling points because they have very strong forces of very strong electrostatic force. Electrostatic is the word used because some of them are positive, some of them are negative. So because the force is because of their
Yeah.
opposite signs, opposite
Yeah.
charges. So that's why we say this is electrostatic force. So because it has a very high electrostatic force, their melting and boiling points are higher because
Hi. Hi.
for anything to be to melt or to boil, all the atoms,
It needs to overcome the electrostatic force.
yeah, everything has to expand. And if something cannot expand because it has very high forces, then it will stay as a solid.
Yeah, so it takes a lot of energy to overcome the electrostatic force.
So table one compares the melting points of several ionic compounds. So 993, one, I don't think you need to remember this, but the melting points are higher for lattices containing ions with greater ionic charges. So if, yeah, this is what you should know. So if you see here, the melting points are higher for lattices containing ions with greater ionic charges. So if you see this has just one positive and one negative, so the melting point is lower compared to Ca2 positive and F negative because this number is higher than just a single positive. So that's why. Similarly, this is sodium and this one has two negative on it. So it's higher than this at least. And this one, both of them have two positive. None of them has one negative or one positive. So that's why it's the highest melting point out of all of them. Because again,
Yeah.
more electrostatic force.
Yeah.
Power of two. So power of two in just one. So that's fine. Uh,
Yeah.
all right. So the melting points, however, lattices containing ions are greater as there is stronger attraction between ions. Ionic attraction also depends on the size of the ions, but in this example, the Na positive and Ca2 positive ions are similar size, so this is not a factor here. Now, there's another factor that they are talking about. If something is like, so what is below sodium positive? What is below in the periodic table? Sodium, below sodium is potassium. No,
Yeah,
potassium. Oh, it's potassium.
potassium.
So if it's something like Na plus Cl minus and something like K plus Cl minus, then the higher melting point will be for, oh, I forgot. Um, yeah. So which one will have a higher melting point? Which, so first of all, which one will have more electrostatic force?
But the ions are the same.
Ions
Like
are,
the charges are the same.
yeah. So there are two things. So one was that both of the if one of them was something like Ka2 positive, then it will be different case. We will know for sure that this one will have more electrostatic force and hence a higher melting point. But what if both of them have the same kind of charges on them, but obviously they have different atomic structures? So if you think about sodium positive, so I'm also a bit confused about this one. Potassium will have more protons, so will it have higher force of attraction for chlorine, or potassium will have yeah, I think potassium will have more electrons, so it will have higher force of attraction between potassium and chlorine, and that's why the higher melting point will be for potassium and chlorine. Let's see if let's see what's the melting point of potassium chloride. First of all, is there something like named as potassium chloride? I don't know. Yeah, melting point of potassium chloride. So it's 770. Oh, we don't know about NaCl. So this is 770. Uh, and what is the melting point of sodium chloride? Oh, not sodium, sodium chloride. 801.
801. So sodium chloride is higher.
Oh, so I was wrong. So potassium
Yeah,
is below sodium.
yeah.
No, I don't know.
I think it's just, wait, what were you saying?
So if you see here, what they are saying, ionic attraction also depends on the size of the ion. But in this example, the sodium positive and calcium 2 positive ions are similar size, so this is not a factor here. All right. This
Not
has
sure.
lower melting point. The reason could be that, okay, the reason could be that the nucleus is further away from the outer shell or something. And also it has more electrons already. So there's a repulsion because of electrons as well. Sodium has less electrons. So because sodium has less electrons, it has more attraction between sodium and chlorine. That could be one of the reasons, and that's why a higher melting point.
Yeah,
Potassium has more electrons, so it has some sense of repulsion between chlorine and potassium electron as well. So that's why a lower. So this is what they are saying. And ionic attraction also depends on the size of the ions. If the size of the ion is bigger, then it means that there will be more electrons, and that I think should mean that I think, if you think about this one, so is fluorine below chlorine or chlorine? So can you see if fluorine is above chlorine?
yeah, it is.
Fluorine is above chlorine,
Yeah,
and for sodium chloride it is 801, and for sodium fluoride it is 993. So again, fluorine has less electrons, and due to less electrons, the force of attraction is more because there will be less repulsion between electrons and electrons. So that's why a higher melting point. I think that's the reason. So look,
yeah, yeah.
smaller the size, more attraction. Which smaller size means more attraction, and
Well, why does it say it depends on the size of the atoms?
yeah, that is why they are saying the size of it. That is
Oh, so the smaller,
the smaller,
the
the more
smaller
attraction
the,
there is. The more
yeah, yeah.
attraction there is. So
Okay.
yeah, but if something has two positive or two negative, then definitely that thing will have more
So
because
the
this,
first Yeah, the first thing is just the charge.
Yes, first thing
And
is
if
the
the
charge.
charges are the same, then the next thing is just if it's
Yes,
the size.
yes. That's it. All right. Solubility. So many ionic compounds dissolve in polar solvents such as water. Polar water molecules break down the lattice, and by polar they mean the things that you were talking about. Polar called
Yeah, like
covalent bond.
yeah.
So polar water molecules break down the lattice and surround each ion in solution. In a compound made of ions with large charges, the ionic attraction may be too strong for water to be able to break down the lattice structure. So if sometimes it's like Na2, sorry, not Na2, calcium 2 positive or something, water may not be able to break them because they have very high electrostatic force. So it's saying in a compound made of ions with large charges, the ionic attraction may be too strong for water to be able to break down the lattice structure. So water may not be able to break it.
Yeah.
The compound will not then be very soluble. Table 2 compares the solubility in water of several ionic compounds, the most soluble compound. All right. So sodium chloride, they show solubility over here. So sodium chloride has more solubility than calcium chloride, which makes sense because it has more electrostatic force. So water was not able to break them. Sodium carbonate uh, solubility is shown here, and then calcium carbonate. Both are two positive and two negative, so they have very strong electrostatic force. So that's why their solubility is low in water. Does that make sense?
Yeah.
All right. A word of caution, solubility requires two main processes. The ionic lattice must be broken down. So the first thing for solubility is that the ionic lattice must be broken down. Water molecules must attract and surround ions. So that is the second thing. The solubility of an ionic compound in water therefore depends on the relative strengths of the attraction within the giant ionic lattice and the attraction between ions and water molecules. For the ionic compound in table 2, this was table 2, right? Yeah. For the ionic compounds in table 2, the attraction in the giant ionic lattice have the greater effect. The attractions in the giant ionic lattice have the greater effect and solubility decreases as ionic charge increases, but predictions of solubility should be treated with caution. So they're just saying that treat this with caution whenever you're trying to predict what the solubility will be. But they're saying again the same thing that the higher the charge on the uh, atoms, it means that they water is not able to break them and they are less soluble, right?
Yeah.
Electrical conductivity. In the solid state, an ionic compound does not conduct electricity, but once melted or dissolved in water, the ionic compound does conduct electricity. So they do not conduct electricity as it is because obviously they are not. So what happens in the water? They are broken down, right? In
Yeah.
ionic, and when they are in ionic form, obviously then what do you need? So how can you get electricity? To get electricity, there should be a flow of negative ions or positive ions, or positive charge or negative charge. So when
Yeah.
it is in a solid form, obviously due to electrostatic forces being stronger, you cannot make the positive charge go one way and the negative charge go one way. But when it is dissolved in water, they are already in their ionic form, and then positive charge can go one way, like, and negative charge it can go the other way. So that's why they're saying when they are dissolved in water, they can conduct electricity. When not dissolved in water, they cannot conduct electricity. Does that make sense?
Yes.
In solid state, the ions are in fixed position. In the giant ionic lattice, there are no mobile charge carriers. So the ions are in fixed position in solid state. There are no mobile charge carriers, so that's why they can't conduct electricity. In an ionic compound is a non-conductor of electricity in the solid state. When liquid when liquid or dissolved in water, the solid ionic lattice breaks down. The ions are now free to move as mobile charge carriers. An ionic compound is a conductor of electricity in liquid and aqueous states. Why? Because it has free to move mobile charge carriers, which are the ions. And there are no mobile charge carriers when it's in solid state. That's why it does not conduct electricity. Does that make sense?
Yeah.
So summary of properties, most ionic compounds have high melting and boiling points, tend to dissolve in polar solvents such as water, conduct electricity only in the liquid state or in an aqueous solution.
Yeah.
This is just, I don't think this is important. Summary questions. I think that was it.